So that was a lot. Any questions for me there?
I do have one quick question, sir, and it's just how often are we going to be using the differential equations
Not,
within this? You
not.
want us to know how to do them, though? Are we going to have like CPs on them at all, or just know that they exist?
Yeah, you'll, in terms of what I want you to feel comfortable working with in this course, it would be these two first. Those are the number ones. Those are the most useful. In this course, I would say this is number two. We're really only going to be talking about circuits in this class to quickly get into the number one or number two common types of equations. And we will mention difference equations, and you'll see a CP or two on them. I'll give some examples of them, but those are the least interesting because they're the least visual. There's so much with an S-plane that you can just see if it's decaying fast or slow. Whereas with a difference equation, all that information is hidden in the differential equation. I want you to be able to get into a differential equation just to bring that part of mathematics that you've already taken a full course into play. But really, from difference equations, we're going to focus on quickly getting it into a transfer function system representation so we can actually work with it. And the same thing for circuits. First thing we'll do is try to get it into that transfer system representation so we can do something useful. Good question. Any others?
I guess real quick to piggyback off that, how often are we going to be using S-plane for graphing, that is? Like, obviously we're going to use the 2D version, but how often are we going to have to put it on a graph and represent it there?
That's not less common than H of S and H of T, but you'll be using S-planes integrally through the rest of the course. S-planes are, you can't visualize H of S directly. H of S is a great mathematical tool, but it has no useful visualization. To visualize it truly, you'd need to have 4 dimensions, and it doesn't. I've never seen anyone who's made any sense of that. So that the two visual ways of seeing what things are H of T's and our S-planes. Our H of T's, they say different things, right? H of T tells about what the system does intuitively in the time domain, and the S-plane says what the system is doing intuitively in the frequency domain. But you definitely need to feel comfortable with S-planes. So if you've got any questions about them, now's the time to ask. Do you want to see a quick example with an S-plane?
That'd be great, sir.
Sure. Let's do, let's say we've been given a circuit and we've analyzed it and found that its system response, its transfer function looks like this. So I've factored it for you. I mean, you would find that it looks like S squared plus 11S plus 10, and then you'd factor it into this. So S-plane representation, it has a 0 at 0, and it has poles at -1 and out here at -10. So what does that mean really fast? Is it going to oscillate? No, because its poles are all real, so it's not going to oscillate. What's its H of S going to look like? This is going to be an exponential decay that's a little bit slow. This is going to be an exponential decay that's fast. How do we know that? Because we could find its H of T, and we know that it's got a little bit ahead of me. We want to find its impulse response, And we know in order to do that, we firstly have to do a partial fraction decomposition of this. And we could do that. We just cover up the s plus 1 component, put in -1 wherever we see s. We'd have -1 over 9. And over here, we'd have, cover up this part, we'd have -10, excuse me, -10 over -9. So our h of t would be exactly equal to -1/9 e to the minus t plus 10 over 9th e to the minus 10t all time.
Is it negative 10 over 9 or is it positive?
Well, let's see. We'd want to find, we cover up this part, and now we're going to plug in -10 here. And
Okay,
so that would give us
sorry.
-10 over -9, which would be 10 over 9. I'm sitting down now. Now I can do algebra. So, so this tells us something about what our waveform looks like, and this is the part that's going to decay away really fast before we really see what's going on. So this is the part we'll actually get to see what it's doing. But you kind of get that from here. Just looking at this, it says that the overall output of the waveform is going to be dominated by this pole because it's closest to the origin. And then if you wanted to convert it to other forms, you could. You could say, all right, so what's its output over its input? We cross multiply, and we see it's s, x of s, plus y of s times s squared plus 11s plus 10. I think I need to, is this class over? No, it's almost over. And then we can convert that into its differential form. We can say that's got to be x prime. I shouldn't have said equals. I should not have said plus. I should have said equals y prime prime plus 11 y prime plus 10 of y. So now we've got a differential equation. We've got a transfer function. We've got a S-plane. Was there anything else? What were the other common representations?
You have h of t down there too.
I'm sorry?
You had h of t down there as well.
Oh, h of t. Yeah, thank you.
And then I guess the last question, just so I'm making sure I'm
Mhm.
unless it's defined by the problem, h of s is generally its output over input, or is it the other way around?
Always the ratio of the out over the in. Always.
Out over-
And the reason for that is that you don't have to memorize that. How do you figure out y of s using Laplace transforms? It's equal to the input times h of s, right? So therefore,
Right.
just divide both sides by x of s, and you have this as being the output over the input. One catch, just as I let you go, that I don't want to see anybody doing is you're going to do it. It happens to all of us. But remember that this is only true in the frequency domain. In the time domain, y of t is not equal to x of t times h of t. What is it in the time domain? How do you combine x of t and h of t in the time domain to get your output?
You convolve them.
Yeah, that's the one I wanted. Okay, that's it for our lesson.